Okay, class, now we're going to, in our formulas for blood vessels, talk about calculating what we call mean arterial pressure. Mean arterial pressure. Mean arterial pressure is the average pressure in the arterial side of the blood vessels. If I put MAP S, MAP being mean arterial pressure, that means for the systemic circulation. Remember the systemic circulation that we talked about. MAP P is the mean arterial pressure in the pulmonary arterial circulation. We're interested really in the systemic in here. Okay. Calculate mean arterial pressure. There are two formulas for calculating mean arterial pressure. One formula explains everything about the components of the pressure. That formula is MAP equals to cardiac output, which I talked about in the heart section, times systemic vascular resistance, which we just talked about a moment ago. The other formula can be, but we can't calculate that one. Cannot be calculated. The other formula can be calculated, but it does not explain everything. That's of the formula called mean arterial pressure equals to diastolic blood pressure plus 1/3 of the difference between the systolic blood pressure and the diastolic blood pressure. DBP stands for diastolic blood pressure, SBP systolic blood pressure. Okay, we go on a little bit. Why can't this formula, MAP, cardiac output size, to be calculated? Answer. Systemic vascular resistance cannot be truly calculated. We talked about it before, earlier in this series of videos. But in order to calculate SVR, you would have to calculate resistance. Remember, resistance is 8 nu L divided by power to the 4th at every millimeter for approximately 56,000 miles of blood vessels. Now think, every millimeter for 56,000 miles of blood vessels. That's impossible. It would take lifetimes to do that. So it's a great formula to explain everything. Remember, cardiac output equals heart rate times stroke volume. Stroke volume equal to end diastolic volume minus end systolic. You know, SVR, we talked about that. So it's a good formula to explain everything about your blood pressure. It's a good formula to understand how to treat hypertension. But it cannot be calculated. Okay. Calculating, again, using the calculable formula, in order to really get an exact number for MAP using a calculable formula, it requires differential calculus, which most of you have not taken. It requires being able to get an exact area under a curve. I'll show you what I'm talking about in a minute. Differential calculus does that. What can be done in calculus can be approximated in algebra. In this course, we'll use the algebraic formula. So if I asked you to calculate MAP, I would give you somebody's diastolic blood pressure and their systolic. And you would use that. Let me add to that. Made a little error here. Times 1/3 of that. Okay. 1/3 of that. So MAP equals diastolic blood pressure plus 1/3 of the systolic blood pressure minus the diastolic. Okay. So, mean arterial pressure, systemic, equals this. It's the average blood pressure. We talked about cardiac output. Now, let's go here then. Okay, here we are. Again, that's the one we would use to get it. All right, this is kind of what you're looking at here. Think about the blood vessels. Think about the cardiac cycle. Go back and study if you forgot it. During ejection contraction, that's when the heart pumps blood to the blood vessels. During that time, it squeezes a high pressure. So your systolic blood pressure, if you say you have a blood pressure of 120/80, your systolic is when the heart is doing ejection contraction. That's only a minority of the time. The rest of the time before you do another one, is the diastolic blood. And the diastolic, so once you do ejection contraction, remember we had those elastic arteries, we'll talk about it again, you're doing a runoff of blood until you get another ejection contraction. So there's only one true systolic blood pressure, we'll talk about this again, but several diastolics. Only one true systolic, but several diastolics. So therefore, the average pressure in your blood vessels would be, since this is so small, we weigh systolic blood pressure very little. Most of the time in the blood vessels, it's a diastolic. Now, when we take your pressure, we're looking at what's the highest it gets, the systolic, and what's the lowest. There are many diastolics, but we're looking at the lowest. Now, you see this area here under this curve? That's that area. In order to truly get mean arterial pressure, you would use differential calculus to get this area under the curve and then divide it. But since we're using algebra, this would be the formula. This approximates the map, this formula here. This approximates the mean arterial pressure. Right here. So this is the one you would actually use. Okay? Now, we do one other thing. Let's know next. Your pulse pressure. Let's talk about the pulse pressure. You can feel a pulse in several areas. Most do the wrist. I'm sure you've felt your pulse before to see what your heart rate is. You can qualitatively say, do I have a strong pulse or a weak pulse? But that's subjective. What one person may consider a moderate pulse, another person may say it's a weak pulse. See, that's subjective. The mass of a pulse, which we call the pulse pressure, is the difference between the systolic blood pressure, upper blood pressure, and the diastolic, lower blood, which we just talked about. It would be the difference between the systolic and the diastolic. Let's go a little further. Why is the math of the pulse pressure the difference between the systolic and the diastolic? When you feel your pulse, your arterial vessels, let's say in the wrist or wherever, swell up and go down. That's what you feel, that pulsatile force, that pulsatile force. The swell up occurs when the heart is pumping blood to the body, which we just said is ejection contraction. That's your systolic blood pressure. The going down is the time after the ejection contraction. It's the interim time between ejection contractions. That is your diastolic blood pressure. So you're feeling this swell up and go down, this swell up and go down. So therefore, to get an actual calculation on it, it would be the difference between the systolic blood pressure and diastolic. Now let's go over here. So let's say your blood pressure was 120/80. Okay? So to get the pressure, then you would just subtract 120 minus 80, which would equal 40. That would be your pulse pressure. Okay? Now, let's say another person had a blood pressure of 200, which is way too high. 200, let's say, over 180. Now, they got a high blood pressure. But look at their pulse pressure. It's weaker than the one 120/80. Because if I do 200 minus 180, that equals to 20. You see what I'm saying? Okay. Now, while we're at it, let's do this. Let's calculate MAP for these two people. Okay? MAP equals to diastolic blood pressure plus, keep hitting the wrong thing, plus 1/3 of the pulse pressure, which is the diastolic blood pressure, minus the systolic blood pressure. Okay, so let's go up. So let's say we do it for the 120/80. Okay, so in that case, MAP would equal, this computer's having a little trouble, would equal, diastolic blood pressure is the lower number. So in this case, 80 plus 1/3 of 120 minus 80, right? So then, if you pull out your calculator, 120 minus 80 is 40, right? So that's 80 plus 1/3 of 40. That would equal to, what's 1/3 of 40? Let's do that real quick. 13.33. So that would equal to 80 plus 13.33. 93.33. Now, you can do it for the 200/180, but that shows this would be MAP and that's pulse pressure. Just to kind of show you how that worked. All right, let's go a little further. The last subject in the formulas is tension on the wall of your blood vessels. Let's do that. What is the technical term for high blood pressure? Hypertension. Pressure in a pipe leads to tension, expandable tightness on the walls of a pipe. The higher the pressure, the more tension. How do we equate pressure to tension? Let's look at the next slide. The formula for tension equals pressure in the numerator times the radius of the pipe divided by 2. So you see, since this is in the numerator, the more pressure in a pipe, the higher the tension, the more pressure. High blood pressure leading to hypertension. Okay? All right? So, we have talked about a whole plethora of things here, going back, to kind of explain wall tension, mean arterial pressure, capacitance, pulse pressure, a whole bunch of stuff. So these videos here on the formulas, keep going back and forward to them as you study the blood vessels. Keep going back and forward to them. And I think it will help significantly. Thank you.